Hello, everybody, and welcome. I'm having a wonderful day. I hope you are too. Let's get started with 1-2 properties of real numbers. See, the very first question is, what is a real number? Well, a real number is the type of number we usually use, such as 1, 15.82, negative 0.1, 3/4, or etc. Positive or negative, large or small, whole numbers, or decimal numbers are all real numbers. They are called, quote unquote, real numbers because, well, they're not imaginary numbers. And we'll talk about those ones a little bit later down the road. Real numbers make up everything, but they do have different categories. Like the very first category that we're going to talk about is natural numbers, and sometimes people call natural numbers counting numbers. And the reason they're called counting numbers is because it's the numbers that we use to count with. Now, normally when I count 1, 2, 3, 4, so on and so forth up. All right, so counting numbers or natural numbers will be the numbers that are basically whole numbers, no decimal, but more importantly, they do not equal 0. 0 is not a natural number. I'm going to actually put a box around this as well. All right, and there's a reason for that. Because then we're going to jump into the next section, whole numbers. See, whole numbers are just like natural numbers, except for natural numbers don't equal 0, and whole numbers include 0. So I'm going to say whole number is equal to 0 plus all of the natural numbers as well. Okay? Integers. Well, notice whole numbers, we're still not negative, but we have 0. So integers is going to be all the whole numbers and natural numbers that are also negative. So includes negatives. There we go. Poorly written, but it still works. So we have a -1, you have -2, yada, 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 as well as 0, 1, 2, on up. Again, everything's starting to fall into line. However, there's one major problem. These are still whole numbers. There is no decimal. So all of these, integers, whole number, and natural numbers, do not have decimals. So no decimal. Okay? No decimals whatsoever. That's where rational numbers come in. Rational numbers finally give us our first glimpse at decimals. All right? You have your 1/2. You have your 3/4. Those are the nice decimals. You have the 1/3, which is basically 0.33 repeated, right? Anything that's a repeating decimal or something that we can write as a fraction will fall into rational numbers. But notice what I said. It has to be able to be written as a fraction. It has to have a repeated answer, repeated decimal, or else this doesn't work. But it's still a rational number if it falls into this. If the decimal doesn't repeat, that's when you jump into the irrational numbers. Irrational numbers are everyone's favorite numbers. Why? It's because that is like your square root of 2. That is a massive decimal that I couldn't tell you off the top of my head. I can get close, but it's not repeating. It's not a pattern. It's just square root of 2. You have square root of 5. Basically, any square root that's not a perfect square is an irrational number. There's also that famous irrational number, pi, that everyone knows. And we also will be talking about another irrational, which is e, which again, you might not pick up on quite yet, but we will be talking about that later on. But in the grand scheme of things, all of these numbers are going to be a part of real numbers. Imaginary numbers are the only non-real numbers. So let's jump into the guide notes. Let's figure out some of the properties of the real numbers that we're allowed to work with. Like, circle the pairs of numbers that are opposites. Well, if I'm talking about opposites, if I say we have 1, what would be the opposite of 1? -1. All right? I would not flip it. I wouldn't do anything. I'm just basically, we're going to make it its opposite. So 7 and 1/7. Those aren't opposites. I'm not going to worry about it. We have -4 and 4. I would say that those are opposites. 1.2 is not the opposite to 2.1. 5 is the opposite to -5. And last but not least, 4 and the absolute value of 4. Absolute value of 4 is different because we have to solve this one out first. So what is the absolute value of 4? Well, 4. 4 and 4 are not the same. Now, I know what you might be thinking, but wait a minute. If I were to find the absolute value of -4, that is also 4. That's right. It's because absolute value is actually not flipping the sign. The absolute value is the distance from 0. So if I were to draw a number line right here, and I said we are looking for the absolute value of a -1, we have 0 right here, you have 1, and you have -1. Well, if I were to figure out the absolute value of -1 and the absolute value of 1, they're saying what is the distance from 0? Well, the distance from 1 or -1 to 0 is 1 unit. The distance from 1 to 0, again, is 1 unit. Both of them have the same distance, and you can't refer to distance as a negative number. You can't go negative distance. It's just not possible. And yes, walking backwards isn't going negative distance. You're just going a distance away from where you started. You're just walking backwards. Anyways, the absolute value of -3 is going to be 3, so the opposite of that would be -3. So the absolute value of -3 is still -3. 1 becomes -1. -17 becomes 17. 1/2, we're not flipping it, so it's still going to stay 1/2. We're just going to make it negative. Now again, we have to simplify. So we have the square root of 16, which is 4. So what is the opposite of 4? -4. And 0. It's not positive, nor is it negative. Therefore, the opposite of 0 is actually going to be 0. Next. The set of real numbers include all rational and irrational numbers. We have natural numbers, whole numbers, integers, rational numbers, and irrational numbers, like I stated before. Can you circle real numbers? Well, real numbers are anything that is not imaginary. So I'm going to circle all of these. The square root of -1 is imaginary. And therefore, it is not real. Circle the real numbers that are integers. Integers, like we said before, can be any whole number. It just can't be a decimal. So if I take a look at the 0, I know the 0 is a whole number. -3 is a whole number. But if I were to take the square root of 5, I would find that that is going to be an irrational number, 1, and 2, it's going to be a decimal. This is not a real number, and 7/8 will give us a decimal as well, so it's not going to be an integer. How does the set of real numbers differ from the set of integers? Well, the set of real numbers contains all real numbers, including integers, as well as rational numbers, which include repeated decimals, and irrational numbers, which include non-repeating decimals. Don't worry, I'll kind of squeeze that down so you can actually see it. There you go. In other words, real numbers is the big picture. Integers is just the person in it. It's just a tiny little portion of all the real numbers that there are. So let's start off with question number 1. Can you classify a variable? Well, your school is sponsoring a charity race. If each participant made a donation D of $15.50 to a local charity, which subset of real numbers best describes the amount of money raised? Well, circle the values that could represent the number of participants making a donation. Sadly, 0 could very well be that thing. Can you have the square root of 5 people? No, you can't have a portion of a person. 3/8 of a person? No, we can't do that. 2.7. Again, you can't have a decimal for a person. You can have 10, however, and you also can have 150. Right? Circle the set of numbers that best describes the numbers you chose in exercise 6. What are these numbers that we chose? Are they counting numbers? Well, yeah, I mean, they are counting numbers, except for there's one major problem. We have 0, so we know that we probably shouldn't select counting numbers. Are these rational numbers? Yeah, I mean, they're all rational numbers, absolutely. But again, rational numbers include the decimals, so can't have rational numbers. What about real numbers? I mean, that's the whole basis of everything, right? This even says it's a subset of real numbers. So we know that, of course, they are real numbers, but again, it doesn't really hone in everything. But whole numbers as hones in perfectly, because whole numbers is the exact same thing as counting numbers, but it starts at 0. And sadly, you can have 0 people donate. This is where I'm going to give you guys a little bit of a break. Take a look at the PowerPoint portion. Make sure you check your answers, and then we'll be on to the next section. What is the graph of the numbers square root of 3? Negative 1.4 repeated. Again, really quick, that little line above that 4 means that it is repeating. So it's basically negative 1.444444, yada, yada, yada. All right? And the 1 over 3. So let's find the integers each number is between. Use a calculator to round to the 1 decimal place. Because the square root of 3 is going to be approximately 1.7. 1.7. The square root of 3 is between 1 and 2, right? Think of the fraction form negative 1.4 repeated, which is approximately negative 1.4, which is also approximately, they can give you two different answers. You could have the 7 over 5, which is the number I prefer, because 1.4, or in this case, I'm sorry, negative 7 over 5, because negative 1.4 is roughly negative 7 divided by 5. Or they might be looking for the 1 and 2/5, which is, again, all negative. So negative 1.4 is between a negative 1 and negative 2. Think 1/3 is between. Everyone's usually going to jump to 1 because they said it, but it's actually between 0 and 1. All right? How can you estimate the square root of 3 without using a calculator? Well, the square root of 1 is 1. The square root of 4 is 2. So if I had to guess, the square root of 3 would probably fit somewhere between the square root of 1 and the square root of 4. So how can you estimate it without using a calculator? Simple. You just have to find the perfect squares that surround the square root of 3. And your answer should be in between theirs, which again is going to be the square root of 1 and the square root of 4, which will be 2. So the square root of 3 is going to be somewhere in between 1 and 2, which we said earlier is 1.7. You can even make that assumption that since this is square root of 3, which is closer to the square root of 4, that we can even say that it's probably going to be after 1.5 or 1.5. Now let's graph them. So we're going to start off with 1.7. 1.7 is going to be very close to that 2. It's not going to be touching that 2 though. But I'm going to draw a line right about there. I'm going to put the square root of 3. The next one, negative 1.4. We said earlier that that's in between negative 1 and negative 2. But it's going to be closer to negative 1. So I'm going to put it slightly closer, because it's almost actually in the middle, to that negative 1. So I'm going to put that negative 1.4 repeated. And last but not least, 1/3. 1/3 is in between 1 and 3, again, but it's going to be below 1/2. So if the 1/2 mark is right here, 1/3 is going to be somewhere around right there, and I'm going to put 1/3. third. Good work. How does the square root of 26 and 6.25 compare to each other using greater than or less than signs? Now, really quick, there is a difference between greater than and less than. Less than, spell out less than. Make it super easy. Less than sign looks like an L. Well, what about the greater than sign? And the greater than sign actually does kind of create a G. It's the end of a G, right? So we do have our greater than. Now, yes, you do have the alligator version that the alligator will eat the larger of the two numbers, but that doesn't really teach you what sign's what. It doesn't really tell you which one's the less than, which one's the greater than. It just shows you which number is larger, right? So if I had to find a perfect square that is close to 26, I'm going to say 25 is the perfect square that is close. Well, what squared equals 25? 5 squared. What about the square root of the perfect square close to 6.25? 6.25 is really, really close to 6, and that would be the square root of 36. So the square root of 36 equals 6. That is close to the 6.25. All right. Use the less than sign or greater than sign twice to compare your answers in exercise 11 and 12. Well, the square root of 25 is less than the square root of 36. And we just said that the square root of 36 is 6, which is less than 6.25. So we know that it's also going to be less than 6.25 right here as well. Since we know that the square root of 25 is less than the square root of 36, which is less than 6.25, is the square root of 26 less than or greater than 6.25? Well, if I were to take the square root of 25 and the square root of 36, I would know that the square root of 26 is somewhere in between the square root of 25 and the square root of 36. Since I know it's somewhere in between, but I also know that the square root of 25 and the square root of 36 are less than 6.25, I know that the square root of 26 will be, in fact, less than 6.25. Which brings up the key concept properties of real numbers. You have closure. A plus B is a real number. If A plus B is a real number, then A times B is a real number. You have cumulative. A plus B equals B plus A. A times B equals B times A. In other words, if I did 2 plus 4, which equals 6, it's going to be the same thing as 4 plus 2, which again equals 6. If I did the multiplying version, 2 times 4 equals 8, well, that's going to be the same thing as 4 times 2, which again equals 8. It works either way. It doesn't change the answer by flipping it around. The next one, the associative. All the associative is saying is basically the parentheses don't really matter. If I group up the A plus B and then add C afterwards, it's going to give you the exact same answer as adding the A after you have already added the B and the C together. Same thing for the multiplication. A times B going first isn't going to change when you multiply it by C, when you have A times the BC that are already being multiplied by each other. Identities. If you add 0 to a number, it stays the number. No matter if you're putting the 0 first or after the number, if you add 0 to it, it doesn't change. Well, the number that you multiply to keep everything the exact same, keep its own identity, will be multiplying by 1. 1 times anything stays whatever that is that you multiply by. The inverse in addition will actually end with 0. So if I were to add a number's opposite, so A plus negative A, you're going to equal 0. Well, multiplication, the inverse actually will not equal 0, so they really harp on that. But instead, it's going to actually equal 1. All right? So A times 1 over A will equal 1. And last but not least, the distributive property. Everyone should remember this one. You take the bars, you got A times B as well as A times C. If you're ever multiplying next to a set of parentheses, you need to make sure you multiply everything on the inside of the parentheses from the outside of the parentheses. So, which one is which? Well, as you can see, it looks like they're just changing the order in the very first one. So this is going to be the cumulative property of multiplication because we are multiplying when you see those parentheses. This one looks like they're changing just the parentheses. So this is going to be the associative property of addition. You have x plus 0 equals x. That was the identity because you're keeping it the same. The identity for the multiplication is also going to be the next one because, again, whenever you start with a number and you end with that same exact number, it's going to be considered an identity. All right? 8 plus negative 8 equals 0. That is the inverse property, and since we're adding, it's going to be of addition. And then you have 5 times 2x plus 1 is equal to 5 times 2x. In other words, they multiplied those two, plus 5 times 1, which again, they multiplied it out. Now that is a drawn out version of what we see right here, but this is still the distributive property, which is the final thing that we have. Right. Which property does the equation 3 times g plus h plus 2g equals 3g plus 3h plus 2g illustrate? Well, it looks like we took that 3 and we multiplied it by the g and the h. Right there, drawing those lines, we know that it is going to be some form of multiplication because we're starting with the g multiplying by the 3, h multiplying by the 3. All right, circle the algebraic equation. The only thing that we really have to change algebraically would be changing that 3 to some form of variable. So which one looks like the original equation, only instead of using 3, it has an a. And I'm going to circle this one. Question number 18, the equation shown here illustrates the distributive property. And we have finally made it to the lesson check. All right, it's the last little bit, so let's get going through it. There are grouping symbols, which is a way of saying parentheses, or you might also see brackets. Both of these are considered grouping symbols. All right. There are grouping symbols in the equation 5 plus w plus 8 equals w plus 5 plus 8. So for question 19, which one of these shows the associative property of addition? If you remember, that's when you start off with a set of parentheses and you just move the parentheses over. You move the grouping symbols over. The only one that starts with parentheses or the grouping symbols and moves it over is the last choice. The associative property of addition is a rule about the grouping of the terms. It is not a rule about the order. Now let's write the terms grouped in each side of the equation. Well, as you can see in the very first set of the equation, you have a 5 and a w. So on the left side, I'm going to write 5 and w. Well, on the right side, we have a w and 5. W and 5. So the things that are grouped happen to be the exact same. So explain why this does not illustrate the associative property of addition. I'm going to say because it doesn't change the terms grouped, but instead just changes the order in which they are presented. So the very last question will be, circle the property that the equation actually illustrates. Well, if we're changing the order, or not changing the grouping, then I'm going to say that this is actually going to be the cumulative property of addition. Congratulations, guys, you made it to the end. That was the final question. Here's the PowerPoint to make sure that you guys answer everything correctly. Make sure you have everything written down appropriately. Save it to your computer so you can see this in the future. And lastly, have a great day, everybody. Stay out of trouble. Don't do anything stupid. And I'll see you later.